Hey there, everyone. Hope you're all doing well today. So today, we're going to get started with the event, Accelerating Diffusion with HuggingFace. So I'm Anish. I work as a machine learning engineer on the growth team at Weights and Biases, which I'll walk through later. Don't want to spoil the fun ahead. But I want to say I'm very excited to be joined with Patrick and Zach from HuggingFace. And so before we start off today's presentation itself, let's talk about what we're going to learn. We're going to learn how you can accelerate your diffusion by using the Accelerate package by HuggingFace and the diffusers package by HuggingFace, a collection of tools that they released that make it very easy for you to do your generative workflows in a very streamlined fashion. With that, you're also going to learn about built-in experiment tracking, model checkpointing, and rich media logging provided by Weights and Biases. So at any point, if you want to engage with any of the speakers here, you have the option to ask any questions in the chat on your right-hand side. And while we're going on, let us know what you think. And at the very end, we'll have a few minutes for Q&A. And looking forward to for all of your opinions about this talk. With that, I'll hand it over to Zach.
Great. Thank you so much, Anish. My name is Zachary Mueller. I am a deep learning software engineer at HuggingFace, and I'm going to be talking to you about the Accelerate library, also known as 3 powerful sublibraries for PyTorch. So as I mentioned, I'm a deep learning software engineer at HuggingFace. I'm also very much an API design geek. I love learning how software libraries are built and how communities engage with them, such as TensorFlow, FastAI, HuggingFace transformers, and whatnot, which all centers around Accelerate. Accelerate is designed to be a library that provides 3 different subcategories. So one is what I'll call a launching interface. The next is a training library. And then finally, the big Model Inference package that is provided, which is sort of the foundations for these big models doing inference on small compute. Now, first, let's talk about this launching interface, because Accelerate is designed to help you train and run Python scripts on any compute. But can't you just do Python run my file? Not quite. So, for example, if I wanted to take a Python file and just call Python some script, what winds up happening is this will use at most a single GPU on your system. In order to actually do what we call multi-GPU training or multi-node training, you have to use a command called torch run out of PyTorch or torch distributed launch and specify how many GPUs you want to use. And nodes means number of computers, and procs means number of GPUs you're using. And then it can get even more complex when you bring in different high-level wrappers, such as deep speed, which has its own command line interface. And so now, in order to have code that can be launched on, GPU, TPU, and what have you, you need to memorize all these different commands. There has to be an easier way. As a result, we have Accelerate Launch. Accelerate Launch is designed to be a sort of central command for you to launch on deep speed, fully sharded data parallelism, multiple GPUs, single GPUs, TPUs, and CPUs without actually having to use the training aspect of Accelerate. You could use Accelerate solely to just make it a simple way for you to launch your scripts. Now, how does this work? Well, as a result, or as it might sound like, we need a way to know what your system has. And so there's a simple command line interface that will ask you a series of questions saying, what type of machine are you using? Are you going to be doing distributed training and other sorts of configurations that we can keep track of and can use quickly whenever we call this Accelerate Launch function. Or don't. You absolutely don't have to go through this very mildly cumbersome command line interface. Instead, you can just use Accelerate Launch and pass in all the inputs that are needed. And what you'll find is these parameters basically fall in line with whatever we would be wrapping under the hood. So for example, with training on multiple GPUs or launching on multiple GPUs, torch run looks like that first line there where we have those n nodes n proc. And the accelerate version of that is passing the multi-GPU flag and the number of GPUs you're training on. Another option for you to do instead is if you don't want to have to pass in the multi-GPU stuff and whatnot, and instead want us to figure out roughly what your computer takes, we have a very quick accelerate config default that will just write a very flat default configuration, finding the number of GPUs you have, and writing this out for you. The last, and personally my favorite part of our launching interface is we have something called the notebook launcher. So before this existed, it wasn't really possible to train on multiple GPUs out of a Jupyter notebook. And so you couldn't make use of, say, Kaggle's new 2 GPU instance that they provide. With the notebook launcher, however, you write a training loop function and make sure that you don't share any or initialize any CUDA memory before you start it, pass in the arguments and how many GPUs you want to use, and then accelerate can go and launch that command on multiple GPUs and still print out everything REPL style directly in your Jupyter notebook. So that was talking about how do we launch these Python scripts on TPUs, GPUs, and whatnot. But when I do that without modifying my code, am I actually going to be training on multiple GPUs? And that answer might surprise you. No, it won't. Because what winds up happening is you need to customize your script in order to wrap around whatever different libraries might need to do this multiple GPU or TPU training. And usually it's large chunks of code. You have to wrap your model around a few things, your data loaders around a few things. Be careful with how batches are done. Accelerate solves this by just saying, use the same code, add in 3 lines of code of our library, and be on your way. Let's look more about what that's like. So here's a very basic training loop, right? You have iterating over a data loader, optimizer zero grading, moving inputs to devices, getting the model outputs, calculating the loss, backwards pass, and going through the optimizer steps and scheduler steps. Let's look at how accelerate would modify this. As you can see, it's basically printed here about 5 to 10 lines of code, but you could, of course, clump this together. I have it here for readability. You essentially add 3 things. You import the accelerator, initialize the accelerator, and call the most important function accelerator.prepare. And in this, you would pass any sort of PyTorch-specific objects. So that would be like your data loader, your model, your optimizer, and your scheduler. And then from here, accelerate will first make sure that the data is automatically pushed to the right device. That is why inputs and targets is commented out there. And then second, replace loss.backwards with accelerator.backwards. With these basically 4 lines of code, accelerate will let you automatically work with distributed data parallelism, PyTorch XLA, or even just regular PyTorch on a single GPU without having to change your code at all between the various setups. But there's also a lot more that we can do with that as well. First, let's sort of go in depth on like what actually happened in there though, because I said we wrapped around a few things, but what? So Accelerator looked at how our configuration is set up. So are we on multiple GPUs? Are we on TPUs? And whatnot. And then the data loader was converted into one that can dispatch each batch onto a separate GPU. Now, I don't mean there's 4 copies of your data at any given time. Instead, as the batch gets pulled from the data loader, it will say, okay, if I have 8 GPUs in a batch of 64, each GPU has a batch of 8. And when all of the gradients are calculated, they'll get clumped together as though you did one batch of 64. Third thing that happened was the model was wrapped in the appropriate distributed data parallelism wrapper. This could either be from Torch Distributed or Torch XLA, as I mentioned earlier, because each of them have their own way of handling the model and specifically the gradients from those model outputs. And then lastly, the optimizer and the scheduler were converted to what we call accelerated optimizers and accelerated schedulers. The TLDR version of this is stepping with the optimizer and the scheduler are a little bit different depending on how your distributed compute is set up. And so we handle all of that for you. Now let's go a bit more into what I was mentioning earlier, the extra benefits that Accelerate can provide. Because first I showed, it can help you centralize your code, but what about all of the other things you might want to do that could require some different setups? You'll notice a trend here where Accelerate has features specifically for that. The first one is what we call automatic mixed precision. When you create the accelerator object, you can specify a mixed precision type, such as brain float 16 or floating point 16. And what Accelerate will do is when we call backward, it will automatically calculate the loss with respect to mixed precision. On top of this, if we're doing mixed precision as well, when you prepare the model, it will also convert the model outputs to mixed precision as well, and have the model be able to handle it, but wrap it so that the model outputs full precision. It's a bit weird, I know, but basically Accelerate will handle full precision for you efficiently without you having to actually worry about any of these little details that I just mentioned. Next is gradient accumulation. This is something that was recently added in the last few months. Gradient accumulation, for those who don't know, is basically simulating larger batch sizes by training over multiple smaller batches and then combining those gradients and averaging them to say, rather than doing a batch of 8, I did 8 batches of 8, so I did a step with 64 items. It lets you train a bit more stable when you're handling these smaller and smaller batch sizes. And one thing we found is when it comes to distributed compute and doing this, gradient accumulation has a lot of steps involved. And so we just decided that Accelerator will just have an accumulate function. You pass the model in, specify the gradient accumulation steps back in the Accelerator initialization, and Accelerator will handle all of this for you and automatically do gradient accumulation, but in a way that's not necessarily too hidden. What do I mean by this? The gradient accumulation layer specifically has a lower level to it because Accelerate is designed to be a lower level library. This isn't going to be a high level framework like, say, Trainer in Transformers or the learner in FastAI, where you wrap around everything and it's a black box. Accelerate is designed to be the lowest part of that, where we expose everything you can do without changing your source code as much as possible. So that gradient accumulation wrapper I just showed does this, which is basically checking if the current batch number is divisible by 4 and we should step, or if we're on the last batch. And if we're not, then there's this accelerator no-sync that gets called. This is a method that really comes from distributed data parallelism called no-sync. So Accelerator isn't actually doing anything, it is the model doing something, and we're just at PyTorch code again. We use the PyTorch no-sync wrapper, call backwards, and then call backwards when the gradients finally sync. And that is what it's truly wrapping around, which is one of the things I enjoy about Accelerate specifically. It's never too much magic, and every piece of thing you might call a magic can be found and explained very, very quickly by either reading the documentation or source code. Now let's talk about that third part of Accelerate, that third sublibrary, big model inference. Or in other words, how you're able to run stable diffusion on your home GPU. So a trend that was starting to come out is more and more big models were being released. And as a result, the average user just had no way to run these big models on their local system. They had to rely on paying for big compute costs, not really using it as much. And as a result, it was kind of left to the experts can use it and maybe in production big companies. But HuggingFace is obviously very big on decentralization of machine learning and deep learning. And so the question became, well, how can we get these models to train and not train, but do inference on smaller and smaller compute? And born out of this by Sylvain Guger was the big model inference framework inside Accelerate. Let's talk about the basic idea here. So in PyTorch, there now exists something called a meta device. The way to think about that is it's a way to load the model into memory without loading the weights in. And so as a result, it's using a small amount of memory at first. And then as an input goes through each layer of the model, you can take the weights of that layer and load it in from, say, the CPU onto the GPU quickly. The input goes through, and then that layer gets unloaded immediately afterwards. And so as a result, the largest memory comes from how big your biggest layer is. And so as a result, Stable Diffusion version 1 could be ran on less than a gigabyte of VRAM versus the multitudes of gigs that it normally would require. So now let's look at what that looks like. How does it look like in the code? So usually you would start off with a situation like I presented before you, where we have a model class, we load in the checkpoint file we want to use, and then we load the state dictionary into the model itself and update those weights. There's two issues with that, though. The full version of the model is being loaded twice. First, when we initialize that class, and then again when we bring in the checkpoint file. For an example of how bad that can go, if, say, we had a 6 billion parameter model, then magically you're going to need about 48 gigabytes of video card memory in order to bring that model in. And the average user, let alone the average gamer, does not have 48 gigabytes of GPU RAM on them at any given time. So how do we fix this? Well, first, we load in that empty model skeleton. Now, with Accelerate, this looks like a function called init_empty_weights. It's a context manager where essentially any PyTorch model initialized under it will have all of their parameters and layers be pushed on this meta device that I mentioned earlier. Now, in its current state, though, don't try and run it and get an inference off of it, because not all tensor operations are currently supported on the meta device. And so as a result, we basically have this data frame of sorts, this empty PyTorch model that we can't do anything with, but it exists and we can load weights into it. So now let's talk about sort of a pre-processing step of sorts in order to do this layer by layer unload and load efficiently. There's something called a sharded checkpoint. So if, say, you're doing like torch.save my model, that wouldn't be able to really work well with Accelerate. Accelerate requires that we save smaller chunks of the model weights into multiple different files that we can load at one time. That way it takes up less, say, CPU memory for us to then be able to move these weights back and forth. So it's not like saying save a quarter of the model on a particular file, and then that entire quarter of the model is brought into GPU memory. It is brought into CPU memory or your RAM. And so the smaller we can get that, the more accessible it can be to smaller and smaller machines. And so what does that actually look like in the code? So the second function is something called load, checkpoint, and dispatch. As it sounds like, we take the PyTorch model that we just initialized with empty weights. You pass in the folder that has your weights that are split up, and you pass in what is called a device map. Now, the automatic device map, which is the default, will tell Accelerate that it needs to find, based on your model's layers, where it can best allocate storage of the layers in memory. That's not GPU memory, that is sitting there without passing any inputs in. All of these layers will then have hooks onto each of them, and that's what, when moving inputs in and out of the layers, will actually move them to the proper devices. But the basic order of it is first it will prioritize utilizing your GPU as much as possible. Then it will utilize your CPU space before finally utilizing your disk space. And the reason for this is all in terms of speed. So one is obviously the fastest because everything is on the GPU at that point if it all fits. If it all doesn't fit, then it's on the CPU, and moving from the CPU to the GPU is kind of fast. It's got some slowdown to it, but it's still pretty okay. And then that third part is the slowest of them all because it has to read it from your computer, right, from your hard drive onto CPU and then move that onto GPU. So rather than one step, there's two. So generally you prefer that if you can keep it between steps 1 and 2, you're better off from a speed perspective and efficiency perspective. Now, all of that put together in a full workflow would look something like so. So you initialize the empty weights in the model, load the checkpoint in dispatch, convert the model to its eval form, and then do some inference. Because again, this is big model inference. Training is not yet there due to a lot of various factors, but for right now, this is inference only. Now, that was a lot of code. Is there a better way to do this? Yes. The transformers library combined with the HuggingFace hub makes this much easier for you to do by wrapping it in the pipeline function class. So this is an example of 10 lines of code, which really are 4, saying specify a task, specify a model. Here we can then also specify that device map parameter I just showed a moment ago. And then to save on even more memory, we can also tell it how we want the torch layers and the data type to be done. So this is like loading things in half precision versus full precision. And so then you can just use this very quickly to perform your text generation. What about stable diffusion though? I mentioned this, right? How do we translate this into doing these awesome things with stable diffusion on low resource? And next we have a demo with doing exactly that with diffusers and weights and biases. I'll hand it off to Patrick now as he can sort of show you what that's going to be like.
Hey everybody. Super excited to speak here today. To present myself real quick, I'm Patrick. I'm one of the core maintainers of the diffusers library. And I just want to give you a short hands-on demo now for stable diffusion and accelerate, and also stable diffusion and weights and biases. So I think Zach gave you a very nice overview now of how accelerate can be used to make your code more efficient. And I just want to show you now how this applies to a real world case. So here's just a quick demo where I'm going to run stable diffusion now on the Google Colab. You can see I'm using GPU. Let's see what I got. I got a T4. Okay, cool. Then you can install diffusers here with pip install very easily. Diffusers also heavily relies on other libraries. So transformers is necessary for stable diffusion because of the text encoder, which is a clip. And then we also have some other packages we like for faster schedulers, like SciPy. And we now also more or less actually have accelerate as a required dependency for diffusers, simply because of the more memory efficient model loading, which I'm going to show you now. Cool. I think they're already installed here in this notebook, and I'm going to use the Stable Diffusion v1.5 here. So you can actually also check it out here. It's a pretty popular model by now. It has over 1 million downloads last month, and lots of demos are built on it. All right, cool. So now what I'm going to show you is just the difference between not using accelerate for loading the whole pipeline and using accelerate. So in the first cell here, I'm just going to run it without using accelerate. What I do here is I pass the model ID, then I tell the model to use the float 16 D type. I don't need a safety checker here for the demo now. And as you can see, I pass low CPU memory usage equals to false. The reason why I do this is because we actually use accelerate now always by default, which means if you don't pass that, you already use kind of the fast way of loading the model with Accelerate. So now Accelerate is disabled. Just for a demo purpose, I disabled here with false. You can see it takes 17 seconds to load it. And the reason now, I think Zach talked about memory. So the memory benefits, actually, I cannot show you. I cannot show you here so nicely now because it's a Google Colab, and I just wanted to focus a bit on the speed part. So what happens, it takes 17 seconds just to load the model, and that can be annoying if you switch out between a lot of different fine-tuned checkpoints. And the reason is actually to a big part because kind of what Zach talked about before is if you don't use Toys meta device, what you do is you initialize a model, and this model is gonna allocate memory for its weights because you're gonna randomly initialize weights. So this memory allocation on the one end takes time. And the second actually important aspect is also when you do this in PyTorch, you also run normally like an initialization. And this algorithm, like having a Gaussian random weight takes quite some time. So now if I just use the default case here, you can see just the loading time, it should drop pretty significantly. So I think we had with 17 seconds, and now I hope it's going to be less. Yeah, you can see 7 seconds, right? So this makes quite a bit of difference because if you switch out models in a web UI, you want it to be fast. That's also why we just have it enabled by default now. If you don't have Accelerate installed and you use diffusers, you actually get a warning now because it's pretty important for us now. Cool. Now let's see what device map auto does. In the next cell here, I actually just do the same thing, but I add device auto. And the difference is that the model will be automatically be placed on the GPU. So you can see it takes a bit more time, but the nice thing now is already on GPU, right? Like the device here is cooler, it's not CPU anymore. And this can be extremely nice when you have multiple GPUs because then Accelerate will automatically distribute the different components on the GPUs. Or if you, as Zach said before, if you don't have enough GPU memory, will actually use both CPU and GPU. So quite often we always just use device map auto because it's pretty convenient. The big design difference here is the pipeline is completely on GPU now, right? So like you load it and it's right away on GPU if you have a GPU. If you don't do it with device map auto, it's on CPU, which is a bit more PyTorchy by design, which is also why this is currently our default. And a nice add-on is adding device map auto. Great. Okay, cool. Now the second part of my hands-on demo is about how you can use diffuse and weights and biases to do some prompt engineering. So what I want to show you here now is just how you can use, I guess, like your subjective feeling for what images are good and what aren't good, and combined with weights and biases, nice visualization. So what we're going to do here now is, first of all, we can take a faster sampler, which is then loaded into the pipeline quite easily here. And now what I want to do is I want to generate a flower garden blend, which is, I think, actually spelled incorrectly, garden. And I want to add different prefixes and suffixes to it. I think if you probably noticed that there's a lot of prompt hacking, prompt engineering going on with diffusion. And it's actually not easy. And some prompts, they work much better just because you add something like beautiful or hyper-realistic to it. And what we're going to do here now is just resample some prefixes and some suffixes. So in general, like these things, like adding, highly detailed or digital painting, they don't really change the content of the image that's being generated, but they will give it a nicer touch. So quite often just adding something like high realistic can make your picture look nicer. Cool. All right. So the weights and biases is already installed. I'm logged in, and now I'm just gonna init a project with weights and biases. So cool. That's Grateful Cloud 3. I want to click on this afterwards. I just want to start my job now. So what I do here now is I just want to generate 25 different images, and the prompts are going to be randomly sampled because I randomly sample a prefix, a suffix. I format my base prompt to have those, and then I run my pipeline. It's also a pretty easy call here. It's just pipe that we initialized before, then you pass the prompt, and then because it's a better scheduler, we don't have to use 50 inference steps, we just use 25. and then the image will be very nicely locked right away on the weights and biases page. And after this is done, so we're generating 25 images here, we also log a nice table for the overview. Cool. All right, let's start this. And now you can see it's generating images, right? 25 steps for every image. And this is also going to be run 25 times. I think while this is running, this should take, how long is this? 25 times 4 seconds, so it's a bit more than a minute. We can probably already jump into the page here. Cool. So what's very nice is you can see the images that are being generated right away here. So this is the zero image, so the first image, and you can also click on it. So it looks actually not bad, pretty nice. And then you can just advance the slider here for the next step. And then I think if I refresh, I'm also gonna get some more. So now you can see I have some more steps here. So that's super nice, right? So in this example, I'm only kind of prompt engineering 25 images, but people are actually, I mean, they spend hours on doing this, right? Also, when you actually do things like when you create movies with Stable Diffusion, you generate hundreds or even thousands of images, and the prompt is super important. So people do this for quite some time, and then it's extremely nice to be able to visualize this here nicely right away on weights and biases. So there's an application for inference now. Another one is obviously training, right? Like when you train, it's pretty important to be able to subjectively kind of state when the model is better, because the metrics we use for image generation, the FAD metric, for example, is not always the best metric when it comes to how good the image looks. The best metric quite often is just predefining maybe like 100 different prompts and then logging them at every epoch. And for this, you can also obviously use weights and biases. All right, I think I should be almost done here, and then I can also check out the table afterwards. All right, cool. This is finished. I think as soon as it's finished, I also have a nice table on weights and biases. I just refresh that. Cool. Okay, and now I have a very nice table here. That's also cool, right? Because here I can now see my prompt that I sampled. So what do I have here? Epic digital painting, and yeah, another one. So then you can also just compare them quite nicely here right away. Like, well, what looks better? If a certain suffix or prefix just always looks better, then you could see this quite nicely here, by the way. Actually, I think they all look. His cinematics were interesting. Yeah, so you can just kind of check that out here very nicely. So it's a very smooth integration between diffusers and weights and biases here. Yeah, I think that's it from my part. I'm just gonna stop sharing my screen. Cool, and then I think we have Anish as a last speaker now, and I can hand it over.
Thanks for that great talk, Patrick. So yeah, let me show you right now, actually, as a perfect allude to how well accelerate diffusers and weights and biases work together. So as we saw on that dashboard earlier, and from the code itself, the code is very minimal to actually work with weights and biases and accelerate/diffusers. In fact, with accelerate, to log all your training information, all it takes is one simple argument of log with equals weights and biases. And so in this, by simply adding in this one line, all of your metrics during training, so I'll be talking about training right now, during training will flow in to your dashboard, and you had to do no other extra work other than log in. And so that means you get things such as your metrics as seen in the charts below, and you can log other things such as a table with your images and some other information about those images and the images itself. And also, this is not shown here, also things such as model checkpoints. And so with one line, you can do all the metric tracking automatically. And nicely, Accelerate actually provides a really straightforward interface to build out extended functionality for a lot of our trackers. So built in is the weights and biases tracker, but if you want to, theoretically, you could add in a lot of complex functionality if you wanted to log very other interesting bits of information that doesn't naturally come as a process of training across the board. So like in this case, if we want to log images, log our model, or finalize all the information that we may be storing during our training and evaluation, we just build that into the tracker itself. And right here, we can see that it just inherits the ability to log all this information directly to weights and biases. So that's very convenient and easy. And so the only change you'd have to make back to your original training code is just changing what you're actually logging with. And so what benefit do we actually get from this? Well, the benefit we get is grabbing that functionality is extremely straightforward and almost feels natural as part of your process. You don't want to write extra function to write extra all the information and metrics or images that are output from your model during training to like be another thing that you worry and manage. Instead, you just build that into the tracking process and have that be functionality that is already part of the trainer that Accelerate is providing. And so with Accelerate, you're getting this extended functionality to go ahead and distribute your work extremely efficiently across your resources and with the data that's provided. At the same time, all the information about your model is being stored efficiently and in a way that, like I mentioned, works well with the process that you're already used to. And so what are some things that weights and biases provides that's useful for our model training process? Well, so we offer a suite of tools. And so one of the integrations we offer and we love to maintain is the HuggingFace one. And so just to give a brief overview, the three ones that I'll talk about today are experiments, artifacts, and tables. And so in general, as we to mention experiment tracking, when doing your modeling, we're collecting metrics about what metrics from our model to help us understand, one, how well the model is doing, and two, understand things about the performance of the model in terms of not only just how well it's doing from the data itself, but also resource utilization and such. And so having all this information stored inside of a CSV becomes really intractable as you scale out the amount of experiments that you have and the amount of people on your team. And so Accelerate provides a really nice interface to scale out your training workflow directly via code. And Weights and Biases lets you organize these things a lot more organizationally too. So you get kind of this nice scale on both ends. And so that's kind of what this shows, that that all of your experiments from Accelerator can all be deposited into one centralized resource that can easily be managed between yourself, and also any team members if you so choose to. And similarly, like for instance, in that example that Patrick showed, every run would theoretically have a nice collection of images in that table. But what if you wanted to try out prompt engineering every day for a year, maybe 4 times a day for a year? That one run quickly becomes thousands of runs. And so being able to manage all the outputs of your stable diffusion into one centralized location and have ability to go through and filter out using interesting metadata is extremely essential for organizational aspects, especially in the deep learning world. And so what this looks like is 3 really simple steps. You start with the biases and you log the things that you want. And so, sorry, not 3 simple, 2 simple steps. Start the experiment and log whatever metrics that you want. And so, like I mentioned, it helps speed up the development cycle and helps you collaborate across your team or your projects itself. Secondly, we have we use artifacts. So best way to think about it is model checkpoints or dataset checkpoint versions, for instance. So in this case, we are able to easily save our trained model and then store it into a location for ourselves to retrieve such that we can go through and be able to see the output of all of our different model training runs in one centralized location also, and make decisions about whether or not we want to use this model for any tooling that we may make down the line. So in essence, this is a nice visual graphic of that. You have data that may go into a model and it spits out something. You want to make sure you track all that information. And lastly, tables. Patrick also showed this in the previous workspace, but tables is our way to query and large tabular data sets and use it to also do interesting analysis of rich media. So I guess even show it directly, here's an example of that. So let's say in the previous one where we're trying out different suffixes and prefixes, I want to say, I want to grab only the ones that were octane renders. So I'm going to say grab only prompts with octane. And now here, we can start to analyze our prompts directly using this table. So we can go in and say, okay, here are all of our octane renders. And so we can go in and actually look at it. If we were to log other fields, we can also do complex behaviors such as group bys and whatnot. So very, very strong table manipulations that also can be utilized to also organize insights in ways that make sense as a table. Sorry, go back here. And so an example of a training run, though. So what Patrick showed earlier was how easy it is to utilize diffusers and weights and biases together for inference. I want to quickly show you how easy it is to also do from training. And so to go back to what I showed earlier, it's as simple as if I want to use weights and biases, I throw in the WAN-DB flag. If I want to extend out the functionality, I can write some code that will inherit the functionality of the original WAN-DB tracker and just pass that in itself. I re-mentioned this just so when I show you the code, it's not overwhelming. But as you see here, you pass in this extended tracker, and now I can log images and log the model. So one example I'm going to be using is this unconditional image generation, which utilizes both aspects of diffusers and accelerate. Would recommend looking at the examples section under diffusers. Has a lot of great examples showing both. But for this one specifically, to just give a head nod to what I mentioned earlier, we build out extended tracker to do a little bit more extra functionality. And to go ahead and actually use weights and biases with your model. So a lot of code to essentially say, hey, we have a model that we're trying to train. So let's make sure we track all the information of our model properly inside of our tracker. And during training, to accelerate, sorry, wrong button. You can see that we log interesting metrics to whatever tracker we're using. So in this case, weights and biases. And during sections of our training, like over here, where we decide to do some evaluation, we can go ahead and grab the ability to log images and use that right away. Sorry, I realized how small the screen is. But as I mentioned earlier, all that's built into a workflow that is no different from what you would already be kind of using with Accelerator. And so with this code, we're able to create a separate dashboard where from here, you automatically get all these metrics logged. But with our extended functionality, we also get to generate these tables that I showed earlier. But in this case, how each of these rows are a different degree of how many training steps was done. So the best example is initially the images looked something like this, and by the end, they look like this. Well, it doesn't look as good zoomed in to the resolution, but they look a lot more Pokemon-like. And so the example I'm showing here is training unconditionally a Unit 2D model to unconditionally generate Pokemon images based on noise passed in. And so if you were to go to the dashboard for your workspace, you can see that just by adding in some extra functionality, like I mentioned with log images, where it's something as straightforward as log a generated image, which is a WAN-DB image, something that we have a first class data type for. And something as simple as logging a model is simply saying log that folder that exists. And so having this general functionality allows us to go in and just add it as a one-liner directly to our training scripts so that when we do things such as evaluation, all of these images get stored in a way that makes sense in context for us for prompt engineering or training or whatnot. So like in this case, we're trying to see how well our unconditional image training is going for all of the different, for this original entered noise. And then we can see over time directly the evolution of this. with the ability to also query row by row every 10 epochs what the generated images also look like, and do that alongside the loss curves, an understanding of what GPU resources were utilized, code that's automatically logged that utilizes that specific concept, and every checkpoint that was generated during the training. So in this case, we generated checkpoints every, I think every 10 epochs also. So we can directly go in here and actually see the different tracked versions of our model, where we have in here the scheduler, the UNet, and the model index to be reloaded directly in as a checkpoint to accelerator. So accelerate and weights and biases work really well together, and diffusers and weights and biases work really well together. And so, as you can see, not only the usefulness of accelerate for distributing and scaling out your workflows in terms of training and your research itself, but you also can scale out your experimentation workflow, your team workflows, and your organizational workflows using weights and biases. Thanks for listening, everyone.